Hello everyone, this is the second part of a lecture on plate boundaries. If you haven't already, I highly recommend that you watch plate boundaries number 1 first. If you have watched that, then you know that that lecture ended with a view of a map of the seafloor that is color-coded by age. So where you see red, of course, is very young seafloor, where basalts of the oceanic crust are being created at mid-ocean ridge spreading centers. And as you move away from those mid-ocean ridges, the crust gets increasingly older, which should come as no surprise if you understand the process of seafloor spreading. What's curious, however, is the fact that the seafloor never gets older than about these kind of dark blue colors here. So, I don't know, 160 to 180 million years old. Why is that? That was the question that I left you with at the end of the last lecture. Well, it's important to keep in mind that as the oceans are spreading apart and the sea floor is becoming older, our planet is not increasing in size or in volume. So if new oceanic crust is being created everywhere you see the red stripe on this map, then old oceanic crust must be being destroyed elsewhere, or else our planet would be continuously growing in size, which we know that it is not. So the short answer is that you don't have any oceanic crust older than about 180 million years old because it is being constantly destroyed in a plate tectonic theory. This is something that we looked at in part 1 as well, and I just want to remind you that as the oceanic lithosphere becomes older, it gets thicker, colder, and denser, and eventually it starts to act at like this heavy ballast that is pulling the entire plate down, priming it to take the dive underneath the overriding plate. And now I'll move. Let me skip ahead here. Known as a subduction zone. Okay, so a subduction zone is a place where two tectonic plates are moving toward one another, and one of those plates is forced to sink beneath another. We call the one that sinks the downgoing plate, and we call the one that rides on top of it the overriding plate. So a subduction zone is what's being shown in this cartoon image, and it occurs when you have a convergent boundary between two plates. So convergent means coming together. Divergent means moving apart. So at a divergent boundary, you get a mid-ocean ridge spreading center. At a convergent boundary, you produce a subduction zone. So for every cubic kilometer of crust that is being generated at a subduction zone at a mid-ocean ridge somewhere on planet Earth, an equal volume of the Earth's lithosphere is being destroyed or taken away, taken back down into the mantle at a subduction zone. So let's think about why that happens. I'm going to go back a slide here, forward again. And you can see that in this cartoon image, it is oceanic lithosphere that is being subducted beneath continental lithosphere. Oceanic lithosphere is almost always the downgoing plate, and that's because oceanic lithosphere is dense, cold, mainly it's because it's dense, whereas continental lithosphere is thick and buoyant, so more like the cork example, whereas the oceanic lithosphere has that carapace of pine board on top of it. So, and it also tends to be thinner. So you've got this thin, dense, cold oceanic slab. When it collides with continental lithosphere, it is always going to be the loser. It's always going to be the one that subducts or goes down. Continental lithosphere will not subduct. It is just way too buoyant. You can't push it down back into the mantle. You might notice in this view of a convergent plate boundary system that lots of interesting things develop at subduction zones. You get the development of deep trenches. You get the development of volcanic arcs. You get the development of accretionary prisms. That's what's shown here. You get earthquakes. We'll look at that in a moment. So there's lots of really important features that develop at convergent plate boundaries where you have subduction occurring. Subduction happens again because the subducting slab of oceanic lithosphere is thin, cold, dense, and primed to sink back into the mantle. And it's not uncommon that over time that subducting slab will start to pull down and roll back, just like what you're seeing here with the anchor in that top picture. I'm not going to spend too much time talking about this. I don't think it's the most important feature of this, of subduction zones. What is undeniably important is the production of earthquakes in subduction zones. Most of the world's largest earthquakes occur here, where one tectonic plate is subducting beneath another. And that's because there is incredible friction that builds up between the overriding and the subducting plates. And for the most part, they remain locked against one another. And that downgoing slab really only moves down towards the mantle in these incremental violent steps, which are earthquakes. You can see that earthquakes occur both in the shallow parts of the downgoing slab as well as in the deep parts. There have been earthquakes that have been recorded down to the mid-mantle at about 600 kilometers depth or so. We call this zone of downgoing earthquakes that follows the subducting lithosphere the Wadati-Benioff zone. So it was first recognized by two very famous geophysicists who noticed that there was like a zone of earthquakes that developed that had a dip angle to it that mostly paralleled well, this is how we figured out basically the trajectory of subducting slabs in the subsurface of planet Earth was based on the locations of these earthquakes. So the Wadati-Benioff zone of earthquakes is an important thing to remember. And you'll see that there are some that also occur in the overriding plate. So you can get big earthquakes occurring at subduction zones. Most of them are going to occur in the oceanic lithosphere of the downgoing slab, but you can get some here in the overriding continental lithosphere. And these can produce tsunamis. They can produce really damaging earthquake events. So like the big event in Japan that happened somewhat recently, what occurred at a subduction zone. Some of the other biggest earthquakes that have ever been recorded on Earth in Alaska and Chile all happened at subduction zones. So in addition to earthquakes, which are not shown on this picture, there's a number of important other features that I want to point out to you at subduction zones. So when the downgoing lithospheric plate descends back into the mantle at a subduction zone, there are going to be some important mineralogical changes that occur in that subducting slab. And those changes are happening because the minerals that make up the rocks here in this slab become increasingly unstable at these higher in pressure temperatures as the slab moves down deeper in the earth. And some of those minerals may have water, not liquid droplets of water, but H2O molecules bound in the solid mineral crystalline structure. When those minerals get too deep or too hot, they turn into new minerals and they give away all of their water. And when that water is driven off of these minerals due to phase changes that are depth and temperature associated, that water comes up into the mantle, because of course any water or vapors or any volatiles that are leaving the downgoing slab are going to be less buoyant than the rocks, more buoyant than the rocks around them, and are going to want to rise up. When that happens, it promotes partial melting here in the mantle of the overriding plate. So where I've put in that green squiggle is the zone where partial melting of rocks can occur thanks to the process of subduction. Once you've created that, that partial melt can rise up. Maybe some of the magma pools here near the moho. Maybe some of it makes its way all the way to the surface where it spews out, becoming a volcanic event. It is common, in fact, it is a feature of all subduction zones, that you get a chain of volcanoes forming on the overriding plate above these melting centers. A great example of that would be the Cascade volcanoes in the Pacific Northwestern part of the United States. So this is what we would call the volcanic arc. Okay, and this is a natural consequence of subduction. You will also develop something called an accretionary prism, and that's this wedge-shaped deposit here of soggy sediment. And accretionary prisms form because the oceanic lithosphere is carrying with it sediments. These are little bits of pre-existing rocks and maybe like the shells of marine microorganisms that are raining down through the water column and onto the seafloor. And you can think about them forming kind of a loose, soggy blanket on top of the oceanic lithosphere. And that stuff isn't going to make it down this tight interface between the two tectonic plates. Instead, it's going to get scraped up along the top here. And so that's what's shown here with this bulldozer. It's going to basically get shoveled off and scraped up into this wedge of material at the interface of the two plates, forming an accretionary prism. The accretionary prism always develops landward of something called a trench. So where one plate takes the dive down beneath another, a long axial hole develops basically in the oceans. So the Marianas Trench is probably the most famous one of these, and it is deeper beneath the surface of the seafloor than Mount Everest is high above the surface of the continent. So these trenches can be exceptionally deep. So here's a view. This is a photograph of the Andes Mountains that I took ages ago from Peru. So in this picture, so look at the cartoon that's shown in the bottom left. It's a cartoon view of a subduction zone system where you have an oceanic lithospheric plate that is subducting down beneath the continental plate. And in this picture, I would be standing somewhere like so, and then looking off in this direction at the volcanic arc. So these big tall mountains that I'm dashing in kind of green here on the cartoon are these mountains here. So these are the high Andean mountains in Peru. Pretty incredible. So these volcanic arcs produce some of the highest mountain ranges on planet Earth. Just as you can form a continental volcanic arc, or one that forms in a continental overriding tectonic plate, you can also have an island arc. And an island arc is one that forms when the overriding plate is also oceanic lithosphere. So the oceanic lithosphere is, of course, covered in seawater, but for whatever reason, this plate on the right-hand side was denser, and the one on the left-hand side, this oceanic lithospheric plate, was less dense. And so the plate on the right is the one that lost the battle and went down the hatch and was subducted. And just as in the case of the last example, that produces partial melting, which makes magma, which rises up and creates big volcanic edifices. And eventually those volcanic edifices may become large enough that they stick up above the surface of the seawater. And so you can get a chain of volcanic islands. And there's many examples of this on planet Earth. One great example is Japan. So here we've got the Pacific Ocean. Over here we've got another oceanic plate. So both of these are oceanic plates. This is ocean, this is ocean. And this dark, very dark feature here, this very dark blue, is the trench. Okay, because remember, dark means very deep. So there's our trench. And this, which I'll put in red here, is the volcanic arc. So it's the chain of volcanoes that's developing on the oceanic plate to the west, And these volcanoes are becoming large enough that they now join together and stick up above the surface of the seawater. So I've created kind of a list of important things for you to remember about convergent boundaries. 1, this is a must. The downgoing plate has to be oceanic. You cannot subduct continental lithosphere. 2, continental lithosphere cannot be subducted. I just said that. 3, the overriding or upper plate can be either oceanic or continental. 4, because of subduction, there is no oceanic lithosphere on the planet that is older than about 200 million years old. 5, because continental lithosphere cannot be subducted, there is some continental crust present on our planet that is nearly the age of the Earth. So our planet is 4.55 billion years old, okay? And there is continental crust that is nearly that old. I've put 3.8 here, but there's actually crust that's even older than that. I've included one little quiz question, which we'll touch on when we talk on Thursday. And that question asks you to name the material that is scraped off of the downgoing slab during the process of subduction. Is it a trench, a volcanic arc, new oceanic lithosphere, or an accretionary prism? So if you want to pause here and think about that question, you can. We'll take a poll and discuss it on Thursday. Okay, the last type of plate boundary that I want to briefly touch on is called a transform boundary. So in divergent boundaries, 2 tectonic plates are pulling apart from one another. In convergent boundaries, 2 tectonic plates are colliding into one another. And at transform boundaries, they're sliding sideways past one another. I have included a little button here for animations. And this is going to serve hopefully as a reminder to you guys to go and check out those animations. If you join me in class on Tuesday, we'll talk about those and maybe look at some of them. Transform faults, again, are places where the lithosphere of the Earth is broken along a fracture, and that fracture becomes a fault because the rocks on either side are sliding relative to one another. But they're not bumping into each other, they're not pulling apart from one another, they're simply sliding past each other. Transform faults on the seafloor that connect different segments of mid-ocean ridges are transform faults. And because of that, earthquakes do develop along them. So you can see the distribution of earthquakes on the seafloor mapping out many of these transform faults. If we take a look at, say, a cartoon picture of how these transform faults develop over time, I've told you that transforms are a natural consequence of long linear features developing at the surface of a body that is spherical in nature, like our Earth. You have to have transform faults, these little tears that separate the long linear ridges. It's unavoidable in a spherical planet. So in this picture, we've got a transform fault that is developing here between points X and Y. So X and Y are mid-ocean ridge features, but notice that they have been slid sideways away from one another. So Y has moved to the right and so has X. Now over time, as plate A and plate B spread apart from each other, that transform, notice that it doesn't grow. It stays the same distance. But it is a transform fault because in the bottom part of this picture, you can see that plate A is moving to the left, whereas directly above that, plate B is moving to the right. So these are moving in opposite directions. They're sliding past one another. This out here is not a transform fault, and neither is this, because above it and below it, the plates are moving in the same direction. So they're not sliding past each other. Perhaps the most famous of all transform faults on planet Earth is the San Andreas Fault. The San Andreas Fault forms the plate boundary between the Pacific Plate to the west and the North American Plate to the east, along much of the western margin of North America. It has its boundary to the north here at the Mendocino Triple Junction, and to the south down here at this triple junction. So it's a long feature. The picture on the right shows the trace of the San Andreas Fault ripping apart part of the Central Californian Carrizo Plain. So it's a really, really distinctive picture, easy to see in satellite imagery. And it is across the San Andreas Fault, the Pacific and North American plates are sliding past one another. So you can see the arrows here showing this. So the Pacific plate is moving north and west, whereas the North American plate is moving south and east. And so as they slide past another, a transform develops. Here's an aerial photo taken of the Wallace Creek area of the Carrizo Plain. It's a very famous photo, and hopefully you're looking at this and the San Andreas Fault is popping right out at you. The San Andreas Fault is this scar that runs across the picture like so. And you can see there are some really interesting features that have been offset by the San Andreas Fault, namely this creek called Wallace Creek. So it's coming down here like that. And then, oh, where does the creek go? If you want to follow that creek, you've got to come all the way down here to catch it again. So the creek has been offset by the San Andreas Fault, like so. And you can see in the picture here, here's a fault, and it's doing the same thing. It has taken this fence and boop, moved it like so. It's offset the fence. And this is just the last thing I'm going to show you before I stop this video. I mentioned before that the San Andreas Fault was bounded by two triple junctions, one up here and one down here. And so I just wanted to define for you what those are. Triple junctions are simply places on planet Earth where three tectonic plates intersect. So you can see on the picture on the left here, we've got a triple junction between the Indian plate to the east, the African plate to the northwest, and the Antarctic plate to the south. We would call this a ridge triple junction because the triple junction joins three mid-ocean ridge segments. Up here, these triple junctions are in the San Andreas example. The triple junctions are a little different. They are transform junctions. We don't need to discuss the details of that right now. I just want you to be aware of what I mean should we talk about triple junctions in the future. Okay, that's it for now, guys. I will see you later.